So, hello and welcome everybody to today's central exercise session. We'll be discussing sheet number 4 today. As usual, we'll be happy to take your questions on our chat channel at chat.tum.de. Please use the channel MA9711-CE. The channel will be moderated, and today's moderator is once again Leslie Fernandez. You may know Leslie from last time, but still I'd like to ask you to introduce yourself briefly for those who maybe haven't had a chance to join us last week.
So, hello, my name is Lesuri, and welcome from my side as well to the central exercises in mathematics for science and economics. And yeah, I will be taking care of the chat. So whenever you have a question, like write it there. If it is easy to answer, I will answer immediately. Otherwise, I will collect it, and whenever there is a pause for the questions, we will discuss it live.
Okay, thanks a lot, Lesuri. So let's dive into sheet number 4. You should now be able to see my screen. Again, please post any questions you have here on chat.tum.de. Use this channel here. And Lesuri will forward the questions to me or answer them right away. So sheet number 4 is mainly about matrices and a few vector spaces associated to matrices and also matrix multiplication. The first problem, C41, is about kernel, column space, row space, and about obtaining bases and dimensions of these spaces. In the second problem, C42, we consider a linear equation with a parameter and see what we can find out about the solution space of that one. And in C43, we'll be concerned with matrix multiplication and explicitly how we can express certain operations that we've applied to matrices or their rows and columns, how we can apply these, how we can express these operations as multiplication of the matrix with suitable other matrices. So let's start with C41 as a warm-up exercise. In C41, we have a matrix A, which is given as 2, 3, minus 2, 2, minus 1, 2, minus 1, 1, minus 3, 2, 1, 4. So that matrix has 3 rows and 4 columns. It's not a quadratic matrix. And the problem statement asks for a basis and the dimension of the kernel, the column space, and the row space of this matrix. So I suggest we start with the kernel. You will hopefully remember what the kernel of a matrix is, just in case you don't. The kernel of a matrix, denoted by ker of A, is defined as all x that can be multiplied to the right of that matrix. So in this case, we need something like 8 times x, and the result of that multiplication is the 0 vector. If you multiply a vector to the right of that matrix, then that means, like vector here, that means you need to have 1 entry for each column of the matrix. Because when you multiply that, each entry of the vector will be multiplied with the respective entry of the column for each row of that matrix. So that means the vectors need to be in R to the 4. We need 4 entries because we have 4 columns in A. So that corresponds to this one here. And the result will be a matrix, the row number of which is determined by the row number of A. So we have 3 rows. And the column number is determined by the columns of the right-hand side. So X is a vector that has 1 column. So we'll have a 3 by 1 matrix as a result. So a vector with 3 entries. And that means the 0 vector here explicitly would be the vector 0, 0, 0. So in general, the kernel is the solution of the system of linear equations, a times x equals 0. Okay, and again, that row number here, that is reflected in the fact that this has 3 rows. So what we have to do to compute the kernel is we need to solve the system of linear equations ax equals the 0 vector. So let's do this. As usual, we'll use Gaussian elimination. So let's write down the matrix once again. 2, 3, minus 2, 2, minus 1, 2, minus 1, 1, minus 3, 2, 1, 4. And the right-hand side is all zeros. I'm not going to write that down because it will not change during Gaussian elimination anyway. So let's pick our first pivot element. Row 1 already has a pivot element here in the first column. So this is a suitable pivot element. We just use that one. And then we want to obtain zeros below that. So to do that, what we have to do is we have to subtract 3 over 2 times the first row from the second one. And we have to add the first row to the third one. So if we do that, we get the following result. We just copy row number 1. That does not change. Then for the second row, we get 3 minus 3 over 2 times 2. That's 3 minus 3. So there's the 0. That's what we wanted. Then we have this minus 1 here. Minus 3 over 2 times 2. 2 times 3 over 2 is 3. So that's minus 1 minus 3. That is minus 4. Then we have 1 here. And here we have minus 1 times minus 3 over 2. So that's 1 plus 3 over 2. So 2 over 2 plus 3 over 2. That will be 5 over 2. And finally, here's 1 again. And 3 over 2 times 2. That's 3. So 1 minus 3. That will be minus 2. So that's the new second row. And for the last row, we just add the first row. So we have minus 2 plus 2, that's 0. Here we have 2 plus 2, that's 4. Here we get minus 3, minus 1, that's minus 4. And finally, 4 plus 2, that's a 6. So that's the first step in our Gaussian elimination. Then for the next step, we choose this here as our next pivot element. And we're going to use row 2 to eliminate the entries below that pivot element. And to do that, we just add the second row to the third one. So what do we get here? We copy the first and the second row. Those are not changing anymore. And for the last row, we get 0. Then it's 4 minus 4, that's 0. Then we have minus 4 plus 5 over 2. Minus 4, that's minus 8 over 2, plus 5 over 2, that's minus 3 over 2. And finally, we have 6 minus 2, that's 4. So as you see, we have these 3 pivot elements here. In our matrix, we have obtained echelon form. So that means we are now ready to write down the set of solutions. This last column here does not have a pivot element. So that means the variable corresponding to that, we call it x4, that's a free variable. And we start solving with this one. And when we take to the third row, this one here, there's the pivot element in here that corresponds to x3. So we can solve for x3. And this equation here in that row that reads minus 3 over 2x3 plus 4x4 is 0. Remember, the right-hand side is 0. So solving that one for x3, we get, let's see, x3 is 8 over 3 times x4. Yeah. Then for the next equation, this one here, there's the pivot element in here as well. That corresponds to x2. So we can solve this for x2. And this equation reads minus 4x2 plus 4 over 2 x3 minus 2x4 is 0. So that means x2 is equal to, let's see, that's 5 over 8x3 minus 2 over 4 or 1 over 2x4, right? We know x3 already. x3 is 8 over 3 x4. So we can use that and substitute it here. So we have 5 over 8 times 8 over 3 times x4 minus 1 over 2x4. And that is the 8 cancels out. So we get 5 over 3 or 10 over 6 x4 minus 1 over 2. 1 over 2 is 3 over 6 x4. So we are left with 7 over 6 x4. That seems to be right. And finally, last one. This first column here, that corresponds to x1, the pivot element here. So we can use that first column and solve for x1. And the equation we get here is 2x1 plus 2x2 minus x3 plus 2x4 equals 0. So solving that for x1 then yields, let's see, minus x2 plus 1 over 2x3 minus x4. And again, we take the results that we have obtained so far. So x2 is 7 over 6 x4. So that's minus 7 over 6 x4. And x3 was, where do I have that here? 8 over 3 x4. So plus 8 over 3 times 1/2. So that's 8 over 6 x4. And then minus x4, well, minus 1 times x4, that's minus 6 over 6 x4. So in the end, let's see, we have minus 7 plus 8, that's 1, minus 6, that's minus 5. So it's minus 5 over 6 x4. Okay, so this is the solution we have. This is x1, this is x2, this is x3, and x4 is a free variable. So that means we can write down the kernel of A as the span, or no, let's be a little slower here, as the following set. So we have x4 times, let's see, x4 itself is the free variable, so there's a 1 here. Then we have x3, that was here, 8 over 3 x4. So here's an 8 over 3. x2 was 7 over 6 x4. So we put down a 7 over 6 here. And for the first position, we get minus 5 over 6 x4. So it looks like this. And x4 is any real number. And of course, you can also write this as the span of this vector here. Let's take out a 6 to make things a little easier. So that's -5, 7, 16, and 6 over 6. Okay. And of course, the span, as you know, is the set of all possible linear combinations of the vectors inside. So if we have just one vector here, that means the span is a set of all multiples, all scaled versions of that vector. So it doesn't really matter whether you scale that vector itself. So we can just forget about the 1 over 6, right? We're taking all multiples anyway. It doesn't matter whether we multiply those by 1 over 6 before we do that. So to make that a little easier, we can just leave out that span here, that 1 over 6, sorry. -5, 7, 16, 6. Okay, so that's the kernel. And that means this set here, without the span, that is a basis for the kernel, because that generates the kernel, obviously. And it's also linearly independent. It is just one vector. So if it's not the zero vector, then it must be linearly independent. And of course, that also means the dimension of the kernel of A is 1. Okay, so that completes the kernel. Before we go on to the row and cum space, are there already any questions about that?
Yeah, well, I mean, there were questions that I kind of like tried to answer, but maybe what it was answered, asked several times, it was why we know that when we have to solve the system of linear equations, the vector of zeros is a vector with 3 elements, so it's in R3.
So how we know that was somewhere in beginning, right? So this vector here, right?
Yeah,
so,
correct.
Okay. So we want to solve the equation system that has these coefficients here on the left-hand side and the pseudo right-hand side of just zeros. And as you can see, we have 3 equations here. So of course we need 3 right-hand sides. That means we need 3 zeros. That's one possible explanation. The other explanation would be if you write the system in that form, A times X equals 0. That means what we do here is matrix multiplication. And if you multiply 2 matrices, then the dimension of the result is always dictated by the dimensions of the matrices that are involved. Let's write that down somewhere. So let's say if we have a matrix, let's call it B and C, and we multiply those 2 matrices. Then let's say B is an M by N matrix. Then we know that C must be a matrix that has n rows, because that middle dimension here, this one here, n and n, that must agree. Otherwise, the multiplication is just not defined. And then an arbitrary number of columns, let's say k. And the resulting matrix, oops, sorry, just a second. The resulting matrix will then have m rows. That's the m coming from the first matrix, from the left-hand side matrix of the multiplication. So that dictates the number of rows the result will have. And it will have k columns. So that k, the right-hand side matrix of the multiplication, that dictates the number of columns the result will have. And basically, we're just applying that. So in this case, we have a 3 by 4 matrix. So that means if we multiply that with something on the right, then the result will necessarily have 3 rows. And the number of columns will be dictated by that something. So if we multiply by a vector which has just 1 column, then of course the result will also have 1 column. And that's why we know by this 3 here, we know that the result must be a vector or a matrix with 3 rows. So hopefully that will answer that question. Anything else?
Yeah, there is a question that it says, can you please explain the affine spaces and affine hull again?
Maybe not as part of, so let's defer that until the end, okay?
Okay.
Doesn't seem a very good fit for this problem.
Yeah, and then it says, is the dimension of the kernel the number of free variables?
So the kernel is the solution space of the system AX equals 0. And as we know, the dimension of that solution space is equal to the number of free variables. So yes, the dimension of the kernel is the number of free variables. Let's write that down as well. So that dimension is equal to the number of free variables in the system AX equals the 0 vector. That's correct, yes. That's it for the moment.
Just one more. Why is X4 free? Because we can't perform any row operations. Like, why is X4 free? Well,
so as we said, each variable of the system corresponds to one column. So X1 corresponds to the first column, X2 to the second, X3 to the third, X4 to the fourth. And the free variables are exactly those that don't have a pivot element in row echelon form. So we have these pivots here. And there's never a pivot to the right of a pivot, at least not in the same row. So this cannot be a pivot. And that's why this column does not have a pivot element. So X4 is a free variable. And the others are not, because X3, X2, X1 do have pivot elements. And of course, at this, sorry, just a second, at this point, we already know the dimension of the kernel, right? We know the number of free variables and the number of pivots. So we can already say what the dimension of the kernel is. So that was the only question. We could answer it right away. If we need a basis, of course, we need to do the solution as we did here. But if the question would only ask for the dimension, we could just stop at that point. Sorry.
Yeah, no, I wanted to say that's all for now.
Okay, great. So let's go on. We still have the row and the column space to solve. So let's see what we know about that matrix for now. So that's not important here. We know the kernel is one-dimensional. We also know the rank of that matrix, of course. Remember we had 3 pivot elements here, these 3. So we know the rank is 3. And as you know, the rank of the matrix is equal to the dimension of the column space, and that is equal to the dimension of the row space. So we already know the answer to these dimensions right now. The rank is 3, and that means the dimension of the column space of A is 3. And the dimension of the row space of A is also 3. Now, the row space and the column space, those are the spaces generated by the vectors that are in the rows and in the columns of A. So let's just write down A once again so we can actually see what happens here. That's this matrix here, 3, -1, 1, 1, and -2, 2, -3, 4. So by definition, the row space of A is just defined to be the span of the vectors in the rows of A. So these 3 vectors here, that span the row space of A. So that's the space spanned by 2, 2, -1, 2. And by convention, if the vectors are not part of a matrix, we usually write them as columns. So 3, -1, 1, 1, that's the next row of A. And then -2, 2, -3, 4, that's the third row. So the row space is generated by these 3 vectors. We know that the dimension is 3, so any basis must have 3 vectors. And that means if that is a generator of the row space, then it also has to be a basis, because we could not delete any element without actually changing the span here. So this here is a basis of the row space of A. As we know the dimension of that row space, and I'm running out of row space actually. The dimension of the row space of A is 3. Maybe I can make that A a little more readable. That. Okay, so we have the row space covered. Let's think about the column space for a minute. The column space is the space spanned by the columns of A. So if we take these 4 columns here, and then take their span, that is going to be the column space of A. So let's write that down just to be complete. So the column space of A is equal to the span of, let's see, we have 2, 3, minus 2 as the first column, 2, minus 1, 2 as the second column, minus 1, 1, 3 as the third column, and 2, 1, 4 as the last column. And as you can see, this is a subspace of R to the 3. And by the way, the row space is a subspace of R to the 4 here. And we know the dimension of the column space is 3. So the column space is a 3-dimensional subspace of R to the 3, which is itself a 3-dimensional space. And that can only mean one thing. That can only mean the column space is equal to R3, right? There is no smaller 3-dimensional subspace of that space because the dimensions agree. So what that means is the column space of A actually is R3. So in other words, in that span, we have 4 vectors, but the dimension is only 3. So that means 3 vectors will suffice for bases, or in other words, 4 vectors are 1 too many. We have to remove at least one of these vectors. I don't see, at least not at one glance, which vector would be a suitable choice here. But of course, I can make my life a little easier here. So the question is asking for a basis of the column space, any basis of the column space. It doesn't say that I have to take these columns here. Any basis is fine. So of course I can take any basis I know for R3. And one possible example would be to use the canonical basis, right? So one possible basis for R3, and thus for the column space of A is the canonical basis just consists of the unit vectors, those 3 unit vectors here in that case, and there we have a valid answer. So no need to work more than is actually requested in the problem statement here. So that's a totally fine answer. Okay. Any questions about row and column spaces?
Yeah, well, basically, there is a general question, how do we find out the dimension of the row and column space? I kind of like missed whether you computed the rank or not.
So the idea is the dimension of the row and the column space are equal to the rank of the matrix. And we did compute the rank before. So we did that here, remember? We solved the system Ax equals 0. And in doing so, we computed the row echelon form. And of course, that also gives us the rank of the matrix. We just need to count the number of pivot elements, 3 pivot elements in this case, and that's the rank of A. So this rank is equal to the dimension of the row and column space, and that's how we know that. And again, if you have such knowledge, then by all means, use it. There is no need to compute that basis and that dimension from scratch if you have that information already. More questions?
I think, well, there is a question, can the basis always just consist of the unit vectors?
That depends on the space that we're talking about. So if we're talking about R3, and as in this case, as a vector space, then that is one possible basis. Well, for example, if you look at the row space here, this one, that's a subspace of R to the fourth, and that cannot consist of just unit vectors. So that's not the same thing as listing any 3 unit vectors of R4. If you think of R3, for example, and take the subspaces generated by a subset of unit vectors like here. So let's say this is R3. Let's say we have x1 here, x2 here, x3 here. Then if you take 2 unit vectors like these two, for example, the space they generate will be that plane here, the x1, x2 plane. And that's, of course, not the same thing as the whole space. And it's also not the same thing as some other plane, right? So any choice of 2 unit vectors always generates one of these planes in the coordinate system. These two, for example, generate this plane here. If you want any other plane, then you cannot use unit vectors as the basis. Yeah, take a plane that is like not this, but just tilt it a little, and you can't generate that using just unit vectors anymore. So that's generally not a suitable basis. In this case, it is, because the column space is the whole space already, and any basis for that whole space will do, and that's just the most simple one I can come up with. Any other questions?
Can we argue for the row space that the row vectors in row echelon form are linearly independent, so the basis and dimension has to be 3?
So if we look at the row echelon form once again here, what we did to obtain that row echelon form was basically manipulations of the row vectors, right? So the vectors here, these row vectors, they span the same space as the original row vectors, and these span the same space as the row vectors here. Because what we did is we took linear combinations of those row vectors. We manipulated that space here. So that means we could also take these 3 vectors, this row and this row and this row. This would also be a valid basis of the row space. And in general, you would just take all rows that have a pivot element, and that would form a basis of the row space. That's correct, yes. You can't do so, however, for the column space, right? Because what you're doing here is you're manipulating the rows. So you don't change the row space, but you do change the column space. You don't change its dimension. That will stay the same, but the space itself might change. And that's why you can't just take these vectors here as a basis for the column space. That will generally be a different space. Anything else?
There is one question that it has been repeated a couple of times. Why do we not have to prove linear independency for the basis of the row space?
Okay, why do we not have to prove linear independence for the row space? Well, the point is we know the dimension. We know the rank is 3. So we know the dimension of the row space is 3. And we do have a generator. There are only 3 rows, right? So the set of rows, these rows here that are a generator, they have to be by definition. And there's only 3 rows herein. So that means if we know that a basis has 3 elements, then these have to be linearly independent. Because if they were not, I could remove one and still have the same space generated by just 2 vectors. And that cannot be the case, because dimension 3 means I need to have 3 elements in each basis. Right? So I can't have a smaller generator than that. So that's the smallest possible generator already, and thus it needs to be linearly independent. I don't have to prove that anymore. But of course, if you want to, I have proven that, yeah? Because what I've done here is I manipulated those rows once again, and I have proven that these rows here are linearly independent. I can just see that in echelon form. But again, once I know the dimension, for whatever reason, and I have a generator that has exactly the right size, then I know it has to be linearly independent. So you could also say a basis is a minimum generator, and then it always is linearly independent automatically. More questions?
Yeah, maybe the last one, could we also prove linear dependence for one of the vectors of the column space span instead of using the 0, 0, 1, 1 so the canonical 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0 vector?
So basically the question is, can we take a subset of the columns as our basis, because it would be nicer to have that? Yeah, and the answer of course is yes, we could. Let's do that. Why not? So again, where's my matrix? Let's copy that matrix somewhere so I can actually see that. Okay, so here's my matrix A. And now we want a basis of the column space of A. And let's say we don't have any prior information. The only thing we know is that the column space is spanned by these 4 columns. So what we need to do is we need to compute a linearly independent subset of these 4 columns. We know the column space is a subset of R3 already, so the dimension can be at most R3. It can, of course, be not larger than the space it's contained in. So we can be sure that the 4 columns here cannot be linearly independent. That would be too large. But of course, the dimension could still be smaller if we didn't know that, right? If we didn't have the rank information, the dimension could still be 2 or 1 or maybe even 0. So let's say we want to find a basis of that column space by hand without any prior knowledge. Then what could we do? Basis of call space A without prior knowledge. What we could do is we could just take these vectors here, those 4 vectors, and then compute a linearly independent subset. And we usually do this by applying Gaussian elimination to these vectors until we have a linearly independent subset plus a number of 0 rows. To do that, it's convenient to write the vectors as rows. So I'm going to do just that. So that would look like this. Basically, that's a transpose of the matrix A. Because what I have to do is I have to manipulate exactly the vectors I'm interested in. And the vectors I'm interested in are these. So I need to manipulate these. And I'm just used to manipulating rows. So I'm going to do it this way. You could, of course, also take this matrix here and then do column manipulations instead of row manipulations. That's totally fine. Only important thing is you need to work on the vectors that you're actually interested in, not on a different set of vectors. So what do we do to get echelon form here? We take this as the first pivot element, and then we subtract row 1 here. We subtract row 1 here, and we add half of row 1 to the third one. So what do we get is the first row is just being copied. The second one will become 0. Then it's -1 minus 3, that's -4. And 2 minus -2, so it's 2 plus 2, that's 4. So here we get, let's see, 0, then 1 plus 3 over 2, that is 2 over 2 plus 3 over 2, that's 5 over 2. And -3 minus 1, that's -4. And finally, the last row is going to be 0, 1 minus 3, that should be -2. And 4 plus 2, that is 6. So hopefully that's still correct. Let's see, the next pivot we could use is, let's say this one here, -4, we just use that. Then what we have to do is we have to, let's see, add 5 over 2 over 4, so 5 over 8 of this, I think, right? -4, yes, that should work. And we have to subtract half of row 2 here. So we copy the second row. And let's see, there's a 0. Then we have minus 5 over 2, that's a 0 as well. And here we get 4 times 5 over 8, that's 5 over 2. Minus 4, that's minus 8 over 2. So we get minus 3 over 2, I think. And finally, 0, 0, and then minus 2, that's a 4. Yeah, and finally you can see we can just add 4 times 3 over 2. That's, I think, 6 times that, right? That would be, no, not 6 times. Sorry. 2 over 3 times 4, 8 over 3. 8 over 3 times row 3, right? That should work. And that will give you the 0 here we want in the last row. Sorry. Once again, 2, 3 minus 2, 0 minus 4, 4, 0, 0 minus 3 over 2, and a row of zeros. So again, we can see that there is 3 linearly independent rows here. So that means one possible basis of the cull space of A would be the independent rows that we obtained here in echelon form, written again as column vectors, because by convention, we usually use column spaces, 0, 0, minus 3 over 2, like this. And one more thing, you will notice we didn't swap any rows here in that process. And that means in the result, the first row is of course equal to the first row. We didn't do anything with that. If we're looking at the space spanned by the first 2 rows here and the first 2 rows here, the span of these will again be equal because that second row here, we only manipulated that by adding multiples of the first row. So these here, the span of these first 2 rows always consists of linear combinations of just the original first 2 rows. And the same is true for the next row. So if we take the first 3 rows, then the span of these is the same as the span of these because we only took linear combinations of the first 3 rows here. And that doesn't change until the very end. So the space generated by these 3 rows is the same as the space generated by these 3 rows. And that means we can also take the original 3 rows. So as an alternative basis, we could use 2, 3 minus 2. That's the same, of course. But then we could use the original second and third row. So 2 minus 1, 2, and minus 1, 1 minus 3. That would also work. And that's because we did not exchange any rows, yeah, to guarantee that property that in the end, the span of the rows 1, 2, 3 is the same as the span of the original rows 1, 2, 3. And that wouldn't be true if you mix in something with row 4, for example, or row 5, or whatever rows we have. And by exchanging rows, of course, we would do just that. And that's why I avoided that. So the idea here is that it works because we didn't do any row exchanges. And we strictly work top down, so to say. Okay.
Maybe one last question that
Yes.
I find it a little critical is that apparently it's not clear why the column space is equal to R3.
It's not clear why the column space is equal to R3. Let's scroll back to where we made that argument. So, well, basically there's 2 things that you need to know about this. The dimension of the column space is 3. We found that out through the row echelon form. And of course, the column space is spanned by vectors with 3 elements. So these vectors are contained in R3, and that means the column space is a subset of R3. And if you think of a 3-dimensional subspace of a 3-dimensional space, then of course those two spaces have to agree, right? If that subspace would actually be smaller than the 3-dimensional space, then that would mean there is still a vector that is linearly independent to any vectors in the subspace. And that means you could find a set of 4 linearly independent vectors. But that cannot be the case in a 3-dimensional space, because the basis, any set that generates that space, consists of 3 elements. So there can't be 4 linearly independent vectors. And that means the column space has to be equal to R3. It's a subspace of the same dimension as R3, so it has to be equal to that space. So that's the argument I'm making here. Okay, I guess let's move on to 4.2 then, so that we have some more time to discuss the questions that may arise there. C4.2, so that's more or less a traditional problem. That is actually a problem that was on one of the exams. I'm not quite sure if that was last year or the year before that, but that is an original exam question. So we have a system of linear equations with a parameter. We have a matrix that looks like this, 2 minus 4, 2. There's a parameter alpha in there, 2 minus 2 alpha, alpha plus 2, 1 minus 3 alpha. And we have a right-hand side vector, 1, 0, 2. And we want to look at the system of linear equations AX equals B. And the problem then asks for determining all values such that the system has a unique solution, infinitely many solutions, or no solution at all. So these 3 cases we have to consider. And then it asks for computing a set of solutions for specific values of alpha. So let's first take care of part A. Determine all values such that the SLE has a certain number of solutions. So what we do to obtain that is we simply have a look at that system and try to solve it, and then see what happens in that process. So let's write down the matrix. And then as part of the tableau, the right-hand side, that's the B vector here. So this is the tableau that corresponds to that system of linear equations. And to solve that, what we can do is we can take this here as a pivot element. There's no alpha in here, so no problems with alpha so far. What we have to do is we have to add the first row to the second row 2 times and subtract it from the third row once. And what we get is when the first row is just being copied, right-hand side 2. The second row will then be minus 4 plus 4, that's 0. 2 minus 2 alpha plus 2 alpha, so nicely enough the alpha vanishes, that's just a 2. Then we have minus 3 plus 2, that's minus 1. And for the right-hand side, we get 0 plus 2, that's 2. And for the last row, we subtract the first one, so we get 2 minus 2. Alpha plus 2 minus alpha, that's 2. And alpha minus 1. And for the right-hand side, we have 2 minus 1, that is 1. Then we take this here as our next pivot element and just subtract the second row from the third. And again, there's no special case we need to take care of. There is no alpha involved in this operation so far. So we copy the first row. We copy the second row. And for the last row, we get 2. And 2 minus 2 is 0. And here we have alpha minus 1 plus 1, that's alpha. And 1 minus 2, that's minus 1. So that's the final tableau that we get. Here's, oops, sorry. Here's a pivot element. Here's a pivot element. And potentially this here might also be a pivot element. And it will be a pivot element if and only if alpha is not 0. So that's the first thing we should take note of. So the rank of that matrix is 3 if alpha is not 0. And if alpha is 0, then the rank is 2. So what happens if the rank is 3 and alpha is not 0? Well, then of course we can solve that system of linear equations here, and we will get a unique solution, right? The rank is 3, so it cannot increase if we add that right-hand side vector here. And that means this case is the one with a unique solution. If the rank is 2, however, alpha is 0. And that means in this case, the matrix looks like this. Let's write that down, 0, 0, 0. And the right-hand side is 1, 2, minus 1. And you'll notice there's a minus 1 here on the right-hand side for the 0 row. So obviously, this does not have a solution, yeah, because that would be the equation 0 equals minus 1. So in that case, we have no solution. And this is the only two cases that can actually occur here. So to sum it all up, a unique solution, we have that if alpha is not 0. So alpha is any real number but 0. No solution. That case occurs if alpha is 0. And the case of infinitely many solutions, that is just not possible in this setting. So that's a case that does not occur. Okay, basically that's the only thing that was maybe a little mean about that problem here. Questions so far?
No, there isn't.
No. Okay, great. So let's go to part B. In part B, we are asked to actually solve that system of linear equations for two specific values of alpha. One is alpha equals 0. Well, we know that already. So the set of solutions for that case here is the empty set. We know that there is no solution in that case. And for alpha equals 1, that's the second one we have to take care of. Well, we know that there will be a unique solution in that case. We just have to compute it. And to do that, we just have a look at this last echelon form here. Let's copy that. And for every alpha, we'll substitute the value of 1 here. So we did the computations in a very general way. So we can just replace the alphas by the value that we want alpha to take. So here's going to be a 1, here's going to be a 1. So those are the alphas. And of course, we can easily solve that system here. So if we're trying to do that, we have 3 pivot elements, of course. And that means we can just solve backwards. X3 is going to be minus 1. Then we have 2x2 minus x3 is 2. So that means x2 is going to be 1 plus 1 over 2x3. And x3 is minus 1, so that's 1 minus 1 over 2. So that's 1 over 2. And finally, 2x1 plus x2 plus x3 is 1. So in other words, x1 is 1 over 2 minus 1 over 2x2 minus 1 over 2x3. So we get 1 over 2. Let's see, x2 is half, so that's minus a quarter. And x3 is minus 1, so that's plus 1 over 2. So that's 1 minus 1 over 4, that's 3 over 4. And so the solution set in this case for alpha equals 1 is the unique vector 3 over 4, 1 over 2, and minus 1. So that's the solution here. And please notice that's not a span of this vector. It's just this one unique vector, not all multiples of that. And that means we cannot scale that, right? It's just this specific set of numbers solves the equation and not any multiple of that. So we need to live with the fractions in that case. Okay, so that's part B. Any questions about part B?
No.
No, wonderful. So you would have done great on that problem here in the exam, I presume. And finally, part C, determine the basis of the kernel as a function of alpha. So now we want the kernel in the general case. Again, remember that we have computed the echelon form already. We used a specific right-hand side for that, but of course, if the right-hand side would have been all zeros, then that would not have changed in any way. So the echelon form still is valid, just with the all zeros on the right-hand side. And that means we can just use that to compute a basis of the kernel, depending on alpha. Well, first thing we notice is this last equation here is now alpha times x3 equals 0. So if you want to solve for x3, then of course we can only do this if alpha is not 0 itself. And that means if alpha is not 0, or if the rank is 3 of that matrix, then we can divide by alpha and we get x3 equals 0. And then of course, subsequently, we'll get x2 equals 0, x1 equals 0. And we would have known that already because in that case, the rank is 3, and that means the dimension of the kernel is 0. So the only element of the kernel can be the 0 vector. Right, so the first case is, again, for alpha not 0, we know the rank of A is 3. That means the dimension of the kernel of A is equal to the number of columns of A, which is 3, minus that rank, which is also 3. So that would be 0. So that is the rank here, rank A, and that's the number of columns of A. So if the dimension is 0, then of course that space consists of only one point. And there's one point that is in every vector space, and that is the 0 vector. So in this case, this would be the kernel. And the remaining case is then, what about alpha equals 0? Well, if that's the case, let's again copy that matrix here with zeros on the right-hand side. Now, if alpha equals 0, we can just substitute that here and here. So we get zeros here. And that means we have a 0 row with 0 right-hand side now. And we only have 2 pivot elements left. So in other words, x3 would be a free variable. And those pivots would then correspond to x1 and x2. And of course, we can again solve that. x3 is free. The second equation would say 2x2 minus x3 is 0, or in other words, x2 is 1 over 2 times x3. And the first equation would say 2x1 plus x3 is 0, or solve for x1, we have x1 is minus 1 over 2x3. So what we get is the kernel of A is then the span of, well, we have x3 as the free variable, x2 is 1 over 2 x3, and x1 is minus 1 over 2 x3. And in that case, we have a span of a vector, so all multiples of that vector, we can again scale that vector. Or we can then just write minus 1, 1, and 2. So just scale by 2 here to get rid of the fractions. So this is for the case alpha is 0. So this set here, that will be a basis for the kernel of A. And then, of course, the dimension of that kernel is 1. Okay, that completes that problem. Any questions on that one?
Yeah, there are a couple of questions that I found them pretty interesting. One of them, it says, when doing this question in the exam, would we have to state that we are changing B into the 0 vector, or can it just be assumed that we are doing this because we are finding the kernel? So whether they have to give like specific explanations on what they are doing or not?
So I'm not quite sure whether I got this question right. Of course, you always have to give a specific explanation of why you're doing something. If it's not obvious, if I'm computing the kernel, then I'm solving, by definition, I'm solving the system AX equals 0. So you don't have to state that every time. That should be obvious from now on, if that was a question.
But they should maybe like specify what they are trying to compute. Like, I mean, now we are computing the kernel. So, I mean, they don't have to say like B changes to zeros, but they have to specify what they are computing.
Yeah, of course. So you should note somewhere that you are now computing the kernel. Yeah. Generally, the more information you give, the better it would be for you. Because unless we just count the result, of course, we usually try to give points to all those steps that you do if you do them correctly. And if the corrector has a hard time guessing what you were actually trying to do, because you may have done it wrong somewhere, then he or she will have a hard time giving you any points, right? If the corrector at least has an idea of of what you were trying to do, and that idea is right, then you might still get a point on the idea, even though your result may be wrong. Yeah, but of course, in order to get that point, you'd have to clarify what your idea was. So anything that's not obvious, you should note that somewhere.
Another question is that why is the dimension of the kernel column minus the free variables? I thought it was rows minus free variables. This is what it is written.
It's not rows minus free variables. So you hopefully remember the rank nullity theorem. That's just what we're using here. The rank nullity theorem basically says the number of columns of a matrix is the same as the rank of the matrix plus the dimension of the kernel of the matrix. So it's always the number of columns or the number of variables of the associated system of linear equations, right? It's not the number of rows. Number of columns is equal to the rank plus the dimension of the kernel.
Right. Another question is that could you maybe once more emphasize the difference between the basis and the span?
The basis and the span. Okay, so let's take this case here. So the span consists of all possible linear combinations of all vectors that are inside the set here. So in this case, the span would include all vectors that are multiples of this one here. So for example, it would of course include this vector itself, It would also include -2 to 4, or it would include 0, 0, 0. 0 times a vector is also a multiple. Or you can also take negative multiples. It would include 1, -1, -2, and any other multiple you can think of. The basis, on the other hand, is a set that generates a subspace and that is linearly independent. So, of course, you can't take all of these multiples of the vector because that would no longer be linearly independent. Basically, what you do is you take the vectors that generate the space and the minimum number of those, right? That's the basis. So the basis is the generator. The span is the space generated by the basis, and that's generally a lot larger. I hope that clarifies the difference.
Then there is a question, it's related on how you write the kernel. Like, I mean, it says, why do we not include x3 as a factor at the first span of the kernel?
Oh, here, we could do that. So if you wanted to, this one here. So you could also write this as the kernel is equal to, is equal to x3. Yeah, maybe I can do this in a more readable way. x3 times 1, 1 over 2, minus 1 over 2, and then x3 in R. So that's the same thing. So this set here is basically the system of all linear combinations of that vector, or in other words, all multiples of that vector. And I just decided to write that as span of a vector because it's shorter. You can also write it this way. Totally fine. Same set.
Okay, then there is another question. It says, is any solution of the system of linear equation A0 a basis of the kernel?
Almost. So in this case, we know that the kernel is one-dimensional. And that means the kernel is spanned by any linearly independent vector that is in the kernel, right? So here, let's write that down. So the kernel of A is one-dimensional. That means the kernel of A will be generated by any linearly independent subset of solutions of AX equals 0 with size 1, or cardinality 1. Say cardinality to make that clear what I mean here. So I need a set of one linearly independent vector that solves the system. And of course, any solution will do that. With one exception, I can't use a 0 vector because that is not linearly independent. Okay, so in this case, here, kernel of A is spanned by any solution of AX equals 0 with one exception. And that is x equals 0. That's not linear independent, so it doesn't span the kernel. Any other will do. Of course, that argument depends on the kernel being one-dimensional. So if the kernel is two-dimensional, then you would need to find two solutions that are linearly independent. If it's three-dimensional, you have to find a set of 3 linearly independent solutions, and so on. So it gets more complicated, but it's also still possible, of course. So you can try to guess solutions that are linearly independent, and for that to work, you have to know how many you need, of course. Okay, any other questions?
Yeah, there are like different, several questions related to the kernel, and like one is, it says, why is the dimension of their 0 vector 0? Because she thought it was -1. Is there, if there is just one solution, there cannot be a span, or, and then there is another one, maybe I read all of them because they are related. Why is the span of the kernel not an empty set if alpha is equal to 0, the dimension is...
Sorry, I didn't get that. Why is the span of the kernel?
So why is the span of the kernel not an empty set if alpha is equal to 0, or not equal to 0? I'm not sure whether the dimension is 0, so there is no kernel, or am I wrong?
Yeah, so that if the dimension of a vector space is 0, that means the space consists of one single point. So problem is if we have a basis of size 1, so if you have a one-dimensional space, then that means that space consists of all multiples of that vector, right? Of all multiples of that vector. And of course, that vector has to be linearly independent, so not 0. So for example, if we have, let's do this in R2. If we have a basis that consists of one vector, maybe that could be this vector here. Then the space itself consists of all multiples of that vector. So the space itself would be this vector, any positive multiple, any negative multiple. So that would be the space, right? So this here is the span, if you want, of this vector. Okay, so that's a one-dimensional subspace. So that does not consist of just one point, but of infinitely many points of a line. A thing like the kernel in this case, where the space was just the 0 vector, that would look like this here. So we have just this point here. That's our S here. That consists just of the 0 vector. And that's a 0-dimensional space because it has a basis of size 0. And that is more or less something that we defined as a convention. A basis of S, of this space here, would be the empty set. So we say the set of all linear combinations of the empty set, that basically is the empty sum, and the empty sum is 0 by definition. Yeah, so more or less that is just a convenient convention here. We just say the empty set acts as a basis for this 0-dimensional vector space, for the space that consists just of the 0 vector. And that's where you can say that is 0-dimensional, because the size of the empty set is, of course, 0. So a 0-dimensional space always consists of a single point. A one-dimensional space would be a whole line. And then in turn, that could not be spanned by the 0 vector, right? That 0 vector cannot act as a basis because it's not linearly independent. Because every linear combination of the 0 vector is again 0 and not just the trivial one. Just have a look at the definitions once again if you're unsure about that. I think I also noted this special convention here when I defined the basis on the dimension. I hope I did.
Okay, I think we can continue.
Great, so let's go on. Exercise 4.3 then, the last one for this sheet. So here we have a matrix. I write that down, but actually the matrix itself is not really important here. What we have to do here is something that works for any matrix. This is just to demonstrate how this works. And the question here is, can you express the following operations on A as a multiplication of A with a suitable matrix? And there's a number of operations on A that are listed here. The first one is we want to express a linear combination of the columns of A with given coefficients. And basically, you know how that works already because we've used that before. So if you have this matrix A here, 1, 2, minus 2, 0, 1, 2, minus 2, minus 1, 4. And now if you multiply that with any vector from the right, a vector like x1, x2, x3. Right? Same thing as we did for a system's linear equations. What do you get? By the rules of matrix multiplication, the result will have the same number of rows as this left matrix here. So we have 3 rows. And the same number of columns as the right matrix, that will be 1 column. So the result will be 3 by 1. Then how does multiplication work? What we do is, for each row of the result, we take 1 row of the left-hand side here and multiply it with the entries in that column. And for each column of the result, we take 1 column of the right-hand side matrix. There's only 1 here, so not much to do. So what we do to compute that matrix product here is we multiply this first row with these coefficients here, and that is the first row of the result. So the first row will then be 1 times x1 plus 0 times x2 plus minus 2 times x3. The second row of the result comes from the second row of the left-hand side matrix, and again, that column. So we get 2 times x1 plus 1 times x2 plus minus 1 times x3. And finally, for the last row, this one here, we get minus 2x1 plus 2x2 plus 4x3. And now if you look at that closely, you can see that here we always have x1 as a coefficient. And these numbers here are the ones that come from the first column of the left-hand side matrix. So this here is the same thing as 1, 2, minus 2 times x1. Right? This is this part here. For the second part, there's an x2 here. And these numbers here, those come from the second column. So what happens here is we get plus 0, 1, 2 times x2. And finally, the x3 part, these numbers here come from the third column. Right, so that is minus 2 minus 1, 4 times x3. So this here is obviously a linear combination of the columns. Oops, columns of A with coefficients x1, x2, x3. So in this case, the desired coefficients are mu1, mu2, mu3. And that means what we have to do here is we have to write A times mu1, mu2, mu3. And that is the desired linear combination of A with those coefficients, or the columns of A, sorry, with those coefficients. Okay, so that does the columns. Let's do the rows next before we take questions. Rows work in a very similar way. Again, we want to have A. Let's copy that somewhere. So this is our matrix A here. And now we want to combine the rows of A. Now, what do we have to do if you do want the columns but the rows? Well, you remember the rows, what governs the rows basically is the left part of the matrix multiplication. So an idea might be to just try to put that vector on the left side. And if you want to do that, we have to do something like this here. Because, so this matrix A here, that has 3 rows and 3 columns. So if the matrix multiplication is defined, then the number of rows of this matrix here must be the same as the number of columns of this matrix here. And that has 3 columns. So that's why we need to write it in this way. If you want the matrix multiplication to be well defined, right? We need the first one to have 3 columns and the second one to have 3 rows. And then the result will be a 1 row, 3 columns matrix. Right, so the result here is going to be a matrix in R to the 1 by 3. So, in other words, a row vector with 3 columns. And what is that row vector going to look like? Well, let's see. Now, what we have to do again is we take the rows from the left matrix and multiply these rows with each column from the right matrix. And each combination of rows from the left and columns from the right gives us 1 entry in exactly that row and column position. Right? So in other words, the result is 1 row, and that will always be a result of multiplying this 1 row here with one of the columns, and each column of the result will be governed by one of those columns. So let's again color those. Let's say the first one is orange here. So left row times this column here, times this orange column, that will be 1 times x1 plus 2 times x2 plus minus 2 times x3. Then if we take the second column, the green one here, that will be 0 times x1 plus 1 times x2 plus 2 times x3. And finally, the last column, let's make that blue. That will be minus 2 times x1 plus minus 1 times x2 plus 4 times x3. So we have a 1 row, 3 column matrix as our result here. Okay, and again, if you look at that closely, what is happening here is the x1, if you look at just the x1 entries, those are the numbers 1, 0, minus 1. Now the x1 entry here, that is always associated with the first entry in each column. So in other words, that's associated with the first row. So what we get here is x1 times 1, 0, minus 2. That is the first part, this part of these 3 columns. Then if we look at the x2 entries, we have 2x2 here, 1x2 here, and minus 1x2 here. The x2 entry, this one, is always associated with the second element in each column, so with this one. So in other words, with the second row. So we get x2 times 2, 1, minus 1. And finally, the same happens for the x3. This entry here is always associated with the third entry in each column. So with the third row of the matrix. So that's x3 times minus 2, 2, 4. And that means what we have here is a linear combination of the rows of A with coefficients x1, x2, x3. So the specific linear combination that we want with coefficients lambda 1, 2, 3, that is just given as lambda 1, lambda 2, lambda 3 times A. Okay, let's see what questions you have about those first 2.
Okay, maybe just for clarification, there is like some confusion with the dimension of the empty set, because apparently it has been understood in some video that the dimension of the empty set is -1, but now it is stated that it is 0. Maybe there is some clarification needed in this.
So again, the empty set is not a vector space because it does not contain the zero vector. It cannot be a vector space. That means it's not a very good idea to associate a dimension with that. It's sometimes done, and in that case, the dimension would be -1. So you just say, well, the simplest vector space I have is the one that contains just the zero vector that has dimension 0. So the empty set contains even less. So we associate dimension -1 to that. And that sometimes makes sense, especially in connection with affine spaces, but we'll not usually do this. So if you want to associate a dimension to that, it would be -1. But we usually don't because we don't consider the empty set a vector space. So 0 is the dimension of the space that contains just one point, the zero vector, and that is generated by the empty set. By the empty set itself is not considered a vector space here. Does that clarify that? Sorry.
Sorry. There is another question related to this exercise, that why does the row x1, x2, x3 have to be on the left of the matrix?
Well, it doesn't. Well, it depends on how you look at that. Let's say like this. So if you want to multiply a vector on the right of the matrix, like we did here, then again, for matrix multiplication, you must make sure that the middle dimensions, so to say, agree, right? So you have a number of rows. That's the outer dimension of the first of the left matrix. A number of columns of that matrix here. And then a number of rows of the second of the right-hand side matrix. And those dimensions, the number of columns of the left and the number of rows of the second matrix, those must agree. Otherwise, the multiplication of those matrices is not defined. You can only multiply matrices where these dimensions agree. So if I want to multiply anything to the right of this matrix A, then A has 3 columns. So whatever I multiply to the right must have 3 rows. So if I want to multiply a vector, it must be a column vector like this one. I need the 3 rows. Same thing for the left. If I have this matrix and I want that to be the right matrix in my multiplication. Again, the middle dimensions have to agree. So in this case, I need to look at the number of rows of that matrix. That's the middle dimension here. So whatever I multiply on the left must have the same number of columns as this matrix has rows. So I have 3 rows here. I need 3 columns here. And that means whatever I multiply here must have 3 columns. If I want to multiply a vector on the left, I must write it as a row vector. Otherwise, it doesn't have 3 columns. 1 row is fine. Any number of rows would do, actually. But I want 3 columns. Otherwise, the multiplication with this matrix would not be defined. I just could not compute that. I hope that was the actual question. Please clarify if it wasn't.
Yeah, and then there is a question that it has been repeated several times. Could we just use the transpose of the matrix A for part B and do it in the same way as in part A?
Of course, yeah. You could just say, well, I know about columns already. So if I actually want to do lines or rows of A, then I could just transpose and then go back to columns. That's fine. You can do that.
I think that's all for now. There is questions.
Okay, great. So the other 4 are basically just applications of what we just did. Once you know that, you're almost good. So part C. Now we want to multiply the 3rd row by 1/2. So to clarify what we want here is we want to start with this matrix here. That is A. Oops. That is A. And we want to transform that into a matrix that has the 3rd row multiplied by 1/2. So the first and the second should not change. And for the 3rd row, I want -1, 1, and 2. So that should be multiplied by 1/2. So how do I get that? Well, what I want here is I want to change the rows of the matrix. And specifically the 3rd one, I want to replace the 3rd one by a linear combination of all the 3 rows where I take 0 times the first one, 0 times the second one, and 1/2 times the third one. So if I'm doing something like 0, 0, 1 over 2 times my matrix, like this here, that would be the same as doing 0 times the first row, then taking 0 times the second row, and taking 1 over 2 times the last row. So that would be exactly the last row I want, right? So this is the last row that I want here. So that way I could get that row. And of course, I want 3 rows, not just this one row. So to get more rows, I'm not just multiplying with 1 row on the left, but I have to multiply with 2 more rows then. The result of this, I want to be the 3rd row of my result. So this needs to be the 3rd row of whatever I put on the left. So let's do just that. And do something like 0, 0, 1 over 2 on the left, times, and then the matrix A. Right, so this is A here. And again, I want the result to be, well, the last row, I got that one right already. And the other 2 rows, I just want to copy those. So I want those to be 2, 1, minus 1, and 1, 0, minus 2. So I need to adapt the first 2 rows here accordingly. And of course, copying a row basically can also be interpreted as taking a linear combination, where I take 0 times all other rows and just 1 time this specific row that I want to copy. So this is what I'm doing. To copy the second row, I want the coefficients 0, 1, 0. And to copy the first row, I want the coefficients 1, 0, 0. Right? So this, the first row of the result will be this linear combinations of the rows of A. So just 1 times the first row. The second row of the result will be this linear combination of the rows of A. So 1 times the second row. And the third row of the result will be this linear combination. So 1 over 2 times the third row. And that's exactly what I wanted here. So basically just have to plug in what we know from A and B already, and you get the right matrix here. Okay, so this one here, this matrix here, is the one you want. And let's do D already as well. So same thing for D. In this case, we want to multiply the second column. So you know, to multiply a column, that means we take a linear combination of just that one column. If you want to combine columns, we have to multiply something to the right of that matrix. So what we do now is each column of this matrix here will produce 1 column of the result. We want the second column to be multiplied by 2. So what do we have to do to obtain this? Well, the second column of the result is produced by the second column of that right-hand side matrix. So we need to put something suitable in here. And what we want as a result is a combination that takes 0 times the first row, first column, sorry, 2 times the second column, 0 times the third column. So this will produce a matrix that has as its middle column 0, 2, 4, right? Exactly 2 times this column here, because that 2 here is always associated to that column. And again, for the other 2 columns, I just need to copy the columns that are already there. Or in other words, I need to take a linear combination that consists of 1 times the column I want to copy and 0 times everything else. So here I copy column 1, like this. And here I copy column 3 like this. So the result is exactly what I want it to be. I just copy columns 1 and 3, and column 2 is multiplied by a factor of 2. So the matrix I want is this one here, and again, this on the left here, that's just A. And it works the same for every possible A. Yeah, the idea is always the same. It doesn't depend on any numbers that I used here. Okay, questions about C and D?
Yes, so there is a question that has been repeated. So can we just not write 1, 1, 1/2? So would that be also like a feasible solution for C?
I'm not quite sure where you go with this. So you want something like
I'm not sure
one like this one here?
Yeah, I think could you also simply multiply the matrix A by 1, 1, 1/2?
So I'm guessing you mean something like this.
Yeah,
again, if that's not what you mean, please clarify. So if you're doing that, then, well, the result will be a matrix that has the same number of rows as this one here. So 1 row, same number of columns as this one, so 3 columns, right? So the result will be a 1 by 3 matrix, and that's not what I want already. I want a matrix that has the same number of rows and columns as A, and I just want to manipulate one specific row out of that. So this doesn't work. Of course, what you could try is, well, if this doesn't work, why not do something like put the same row everywhere, right? Let's try this. And again, that would work in terms of giving you a valid matrix multiplication, but it would not give you the right result. What this would do is, it would give you a result where the first row is a linear combination of the rows of A here with these coefficients. So the left-hand side always gives the coefficients for the rows on the right, if you want to, right? So that means the first row would then be a combination where you take the first row plus the second row plus 1/2 the third row of A. And you would do the same thing for all the rows. And that neither gives you the correct third row, nor does it give you the correct first and second row, which are not to be changed in this problem statement. So no, that would not work. Again, if that's not what you meant, please clarify.
And so far, there isn't more questions.
Okay, so finally, let's have a look at E and F. And again, that's just applications of what we did already. So in E, we want to swap the first and the second row. And again, the question is, can we interpret that as taking linear combinations? So basically what we want to do is, we want to not change the third row. Let's start with that one. We already know how to do that. Not change the third row means we just take 0, 0, 1 here, and the result will then have the third row copied like this. And we want to change the first, or exchange the first and the second row. So in other words, we want the new first row to be equal to the old second row. So that's the idea here. New first row is equal to old second row. Well, what does that mean? That means the new first row is a linear combination of the rows of A with coefficients. And well, what do we take here? We want 0 times the first row of the old matrix. We want 1 times the second row and 0 times the last row. So we can just view this assignment as a linear combination where we just take the new row that we want, and that's the old second row. So in other words, we put in 0, 1, 0 here. And that means we only take the second row into the new first row. So that yields exactly this exchange. Yeah, so it's this point here. And of course, we can make the same point for the new second row. The new second row is exactly the old first row. And that means we want a linear combination of the rows of A with coefficients. So we want just the first row. That means 1 times the first row, 0 times the other 2 rows. So the coefficients are 1, 0, 0. So we just need to use those 1, 0, 0. And then we get exactly the old first row into the new second row, right? So again, we just need to come up with the right linear combinations, in this case of the rows, and it all works nicely. And F is almost the same thing. Here we're swapping the first and the third column. So this time we're working with columns. If we want to manipulate the columns of A, you know we need to multiply with something from the right. We're changing the first and the third column, so we're not changing the second column. So we just keep that. We can do that by just putting the suitable unit vector here in the second column. And exchanging the first and the third column basically means I replace the first column by a linear combination that takes 0 times the first, 0 times the second, and 1 times the third. So like this here. So this would give me -2, -1, 4. That's this one here. The second column doesn't change. Let's enter that one as well. And the new third column is the old first one. So I want a linear combination that takes 1 times the first column and 0 times the others. So I will get something like this. Right, so this is the old first column. Again, same idea. I'm just taking the suitable linear combinations. So basically all you have to understand is that multiplying from the left, matrix from the left, is like taking combinations, linear combinations of the rows, and multiplying something to the right of a matrix is the same thing as taking linear combinations of the columns of the matrix. And then you just need to come up with the right linear combinations to do your manipulations here. So, questions?
So there is a question that it says, if the question of D would be to multiply the second row by 2, it could be the same solution as multiplying the second column. How is this possible?
Multiplication of the second row by 2. Well, we know how to do that by now. So if you wanted to do that, let's say this is part G. Multiply second column by 2. Again, this here is A. We want to multiply columns, so we need to multiply from the right. Second column means we want the vector in the second column, and multiplying by 2 means taking 0 times all the other vectors and 2 times that column. So this is this matrix here. And copying all the rest. We can do this way. And of course, you notice that this is exactly the same matrix that we used for multiplying the second row by 2. The difference is that we now have to multiply from the right. If you use this matrix, multiply from the left, then it works on rows. If you multiply from the right, then it works on columns. So this here, just to write down the result of this is second column is multiplied by 2. Did I get that right? No, actually I mixed that up, right? Yes. Okay, sorry. So this is the second column. What you wanted, I think, was the second row. Because we did the second column.
He got what you mean. clear.
So let me just write down that for the sake of completeness. So again, this is A here. And if I want to multiply the second row of A by 2, then I can use the very same matrix. I copy the first and the third row. And now I need, as the second row, I need 0, 2, 0. And that will multiply the second row of A, yes. So the result would be 4, 2, minus 2, okay? So you'll notice the matrix here, this one and this one, that's the same matrix. But in this case, you multiply it from the right. In this case, you multiply it from the left. And the result is different. So the order of matrix multiplication matters. That gives you different results. Okay, more questions?
So far, there isn't any more.
Okay, wonderful. I can see there are 2 mentions in chat somehow. I don't really know what you, oh yeah, okay, you answered that already. So again, for everyone who wants to ask questions, please make sure to ask your questions on our chat channel, not on Zoom chat. We don't generally look at the Zoom chat. Okay, if there's no more questions, then I guess we can conclude this central exercise session. So thank you all for participating. As usual, I hope to see you in the tutorials on Thursday. And of course, I hope to see you next Monday in our next central exercise session. Thanks a lot to Lesuri for moderating today.
My pleasure.
Good, so goodbye.
So.